Hello everyone, Chapter 4, Lesson Charlie, Methods for Solving Trigonometric Equations. Our objectives today are going to be pretty simple, much like Lesson B, solving trig equations using a variety of strategies and then just a bunch of practice. So let's visualize what we're about to do here. We're going to be taking a trig function, say for example some form of sine or cosine, and we're going to be solving for a value. For example, I might say sine of x is equal to negative 1/2, right? Where the negative 1/2 is the red line. And what I'm attempting to do is find angle values, right? Angles, let's call that theta 1, theta 2, etc., for which it's true, right? What theta values give me an output of negative 1/2? Now, clearly you can see if it's a sine function or cosine function or any function for that reason, it's possible it could have an infinite number of solutions, right? So typically what we do is we put a window on it saying, okay, solutions from 0 to 2 pi. But we can also find representations for these solutions that would cover all possible solutions. So we're going to be covering finding a finite number of solutions within the window from 0 to 2 pi, or an infinite number of solutions using a different notation. So let's get started. All right, so in the 4 examples I've got here, I'm going to solve the equation giving solutions for x within the window from 0 to 2 pi. Notice that I am not inclusive here on 0, so I'm not going to include 0, but I will include 2 pi if it's a possible solution. So let's solve the first one. It says 2 sine x minus 1 equals 0. So I'm going to add 1 and divide by 2. So if I add 1 and divide by 2, I get sine of x equals 1/2. Now, on the unit circle, that happens in 2 places within the window from 0 to 2 pi. That happens at the x value equal to pi over 6, and it also happens at the x value 5 pi over 6. Okay, so those 2 values would satisfy that equation. Let's look at number 2. Number 2, I see that sine x plus square root of 2 equals negative sine x. I'm going to do a quick manipulation and add sine x to both sides. And what I will get is 2 sine x plus square root of 2 is equal to 0. So continuing, what I'm going to do is subtract the square root of 2 and divide by 2. So I am now asking myself the question, where is the sine equal to negative square root of 2 over 2? That happens in 2 places, in quadrant 3 and quadrant 4. The x values for that would be 5 pi over 4 and 7 pi over 4. Okay, again, you could validate that or verify it by plugging those values back into the equation and showing that they are equivalent. Let's look at number 3. Adding 1, dividing by 3. I see that tangent squared x is equal to 1/3. If I take the square root, I see that tangent equals plus or minus the square root of 1 over the square root of 3. Okay, now that's going to happen in 4 places. All right, let's look at those 4 locations on the unit circle. Ooh, good circle. Good circle. There we go. Okay, so the tangent would be 1 over root 3 at an angle of pi over 6. It will be negative 1 over root 3 at an angle of 5 pi over 6. It will be positive. Remember, tangent is positive in the first and third quadrants, and tangent is negative in the second and fourth quadrants. And there's some symmetry to this. You guys can see that this would be at 11 pi over 6. So my solutions to the following are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Okay, let's look at number 4. Cotangent x cosine squared x is equal to cotangent x. Now, if you ever see two different functions. So I've got cotan and cosine here. There's no identity that ties them together. So what I'm going to do is I'm going to subtract cotangent of x over to the left side. And when you get in a situation like this, it's really smart to factor out a cotangent, cosine squared x minus 1. And now I can use the zero product property similarly to how I would have done something like this, right? I would have set x equal to 0 and an x squared minus 1 equal to 0. So I'm going to set cotangent of x equal to 0, and I'm also going to set cosine squared x equal to 1, minus 1 equal to 0. Okay, so the cotangent of x is equal to 0 at pi over 2 and at 3 pi over 2. Okay, and cosine squared x is equal to 1 at 0. Oops, hold on. I'm going to miss an answer here. Cosine of x is equal to plus or minus 1 at the following values: 0, pi, and 2 pi. Now, I'm not going to include 0, right? I'm not going to include that due to the fact that we didn't want to do that at the very beginning. We said the window from 0 to 2 pi, not including 0. Now, the one thing I do need to make sure of is that cotangent is defined at all of these values. Cosine is defined everywhere, but cotangent has asymptotes at certain locations. So the cotangent at pi and 2 pi does not exist, okay? So cotangent of pi does not exist. Therefore, pi is not a solution. It's an extraneous solution. And the same thing is true for cotangent of 2 pi. That does not exist. Therefore, that is not a solution. So the only two solutions that we have here are pi over 2 and 3 pi over 2. Okay, let's backtrack and make sure we didn't have an issue with any of these others. We wouldn't in number 3. Tangent is undefined at factors of pi over 2 plus pi. Sine is defined everywhere, as well as in number 1. So we're good. You got to be careful, though, when you come to a function that has discontinuities like cotangent or tangent. All right, let's keep moving. Okay, we're going to up the difficulty level just slightly. We're going to require some factoring on this next set of questions. So in number 1, I'm going to factor, and very similar to normal factoring with polynomials, I'm going to use the same idea. So 2 sine x and sine x. And I'm going to multiply by a -1 and a +1 here. That would be factored for 2 sine squared x minus sine x minus 1. Now I set each of these individually equal to 0. If I set that equal to 0, sine x would equal -1/2. And if I set this other one equal to 0, sine x would be equal to 1. Now in this case, I'm going to find the solutions between 0 and 2 pi, and I'm going to show you how to then find all possible solutions. Okay, so where is sine x equal to -1/2? That is at x equals 5 pi over 6, and, not 5 pi over 6, 7 pi over 6, and at 11 pi over 6. And sine is equal to 1 at 3 pi over 2. Now, what we want is all coterminal angles to these. Therefore, our solution set is going to be 7 pi over 6 plus 2 pi as many times as we want it, right? That k could be any integer value, positive or negative. I'll write that out in just a second. So 7 pi over 6 plus 2 pi as many times as we want. 11 pi over 6 plus 2 pi as many times as we want. And 3 pi over 2 plus 2 pi as many times as we want, with k in the integer set. That's set z, right? K in z, where z is the set of all positive integers. All right, so the all integers. So -3, -2, -1, 0, 1, 2, 3, and on in both directions. Okay, so your solution set is the following right here. Okay, awesome. Let's look at number 2. Now, at number 2, the first thing I need to do is write sine squared as 1 minus cosine squared x. It's going to get everything in terms of cosine, which will allow me to factor much easier. Okay, so I'm going to distribute the 2 and then combine like terms. That'll give me negative 2 cosine squared x plus 3 cosine x, and then the 2 and the negative 3 will make a minus 1. Now I don't like factoring, so when there's a negative leading coefficient, so I'm going to move it all over to the other side. And now I can factor. So I'm going to have a 2 cosine x, and I'm going to go minus 1 and a cosine x minus 1. That should be factored. When I set these equal to 0, cosine of x will equal 1/2, and cosine x will be equal to 1. Okay, this yields for me angle measures. Cosine is 1/2 at pi over 3. That's in quadrant 1, and 5 pi over 3. That's in quadrant 4. Cosine equals 1 at 0 pi or 2 pi. I'm going to put 2 pi here just to have a nice number there instead of 0. And I'm going to find all possible solutions. My possible solutions would be pi over 3 plus 2 pi k, 5 pi over 3 plus 2 pi k, and 2 pi plus 2 pi k, where k is in the integers. Outstanding. Okay, let's look at the next one. Okay, so cosine x plus 1 is equal to sine x. Okay, in this next problem, there is no nice way to be able to factor in order to write this equation in a form that we could write it all in terms of sine or cosine, unless we do one kind of fancy move, and this is very much so based on experience, but I'm going to square both sides. If I square both sides, I am technically keeping the expression equivalent. Now, I do have to be aware of extraneous solutions. However, I'm going to do this. So cosine squared x plus 2 cosine x plus 1 would be foiling that left side. On the right side, I got sine squared x. And what I'm going to do is I'm going to rewrite sine squared x as 1 minus cosine squared x. Now, some of you might be confused, like, why are you working on both sides? I can work on both sides if I'm trying to find the solutions to the equation. I'm not trying to verify that one side equals the other. So I'm going to go ahead and bring the right side over to the left. That means I'll have 2 cosine squared x plus 2 cosine x, and then the ones will reduce, so that should equal 0. Now I can factor this, pulling out a 2 and a cosine x. That leaves me with cosine x plus 1. And now I can use that zero product property. If I set this equal to 0, 2 cosine of x equals 0 when x equals 3 pi over 2 or pi over 2. Okay, and likewise, cosine of x plus 1 equals 0 when cosine of x equals negative 1. And so that would be true when x equals pi. Okay, so a couple ways I can do this. I know these are my 3 solutions. I know that cosine and sine are both continuous for all values of x. Therefore, I don't have to worry about the extraneous solutions. But what I'm going to do is I'm going to rewrite my solutions. X equals pi plus 2 pi k. But I'm going to rewrite this all as one solution. So I'm going to write pi over 2 plus pi k. That will cover 3 pi over 2 and all iterations of it for all values k in the integer set. So I could write it like that, or I could write just a little bit more work and then pi over 2 plus 2 pi k, and then 3 pi over 2 plus 2 pi k. So you can see that in my solution set, this covered both of these, okay? You can do it either way. This is just a little bit simpler way to do it. Okay, so let's do this last one on the slide. Secant squared x, recall, secant squared of x is equal to 1 plus tan squared x. That's where I'm going to find my solutions here. And I'm going to subtract the 4 over to the left side and combine like terms. So I'm going to get tangent squared x minus 2 tangent x minus 3 and factor. Let's see what we can do here. That'll be tan x and tan x. And I'm seeing a minus 3 and a plus 1. So this will be an interesting solution set. I'll show you why in just a second here. But I want to know where tan x is equal to negative 1 and where tan x is equal to 3. Well, this is a traditional solution set here. Tan x will be negative 1 at the two values, 3 pi over 4 and 7 pi over 4. Okay, but tan x equals 3 when at the arctangent of 3. Now, that's not a unit circle friendly answer. That's that would require your calculator. Okay. However, we can still utilize it in just a second here. So I'm going to say my solutions are 3 pi over 4 plus 2 pi k at 7 pi over 4 plus 2 pi k, and at arctangents of 3 plus pi k. Now, you might be asking why plus pi k, because arctangent is 3. Let's say the arctangent is 3 here, right? Let's call that theta 1. It's also going to be 3 down here at theta 2. So this is covering two solutions forever. Okay, it may or may not make sense, but let's say that the tangent is 3, right? Or the tangent is negative 3 over negative 1. Those two angles are going to yield the same tangent values, which means I would add pi to get from one to the other forever, or the other way around. Okay, and these could have been combined. These two could have been 3 pi over 4 plus pi k if we had wanted it to be written that way. Okay, those are some, that's pretty deep stuff, but again, let's keep moving forward and let me know if you got any questions. Okay, so now what I'd like to cover here on this last slide, and we'll go back to solution set between 0 and 2 pi, is I want to bring notice to this is no longer cosine of x or cosine of t, it is cosine of 3t. So what that's going to do is that's going to provide you a horizontal shrink of the function, which means there will be 3 times as many solutions as there would have been in a normal period, right? So check out this graph of cosine, right? Here's the graph of cosine from 0 to 2 pi. Let's say I wanted to know where it equals, 1 over root 2. Okay, if I do a horizontal shrink by a factor of 3, what's going to happen is there will now be, instead of 2 solutions, there will be 1, 2, 3, 4, 5, 6. So if we take b and we change it from 1, that will tell us that there will be 2b solutions. I don't know how to spell solutions right now. That's the word solutions, okay? So whatever b is, there will be 2b solutions on that set, okay? Now that might be slightly different for a tangent. Typically, this is within one period, so don't equate that to tangent and cotangent, only to sine and cosine. Okay, we'll talk about tangent in a minute. So let's look at the following, and for just a second, ignore the 3 on the inside, okay? cosine of 3t would equal 1/2. Okay, so where is the cosine 1/2? Well, the cosine is 1/2, positive 1/2 in two locations. One of them is pi over 3, and one of them is 5 pi over 3. Okay, now, if we analyze this, of course, we're going to add, and now just bear with me, we're going to add 2 pi k onto each of these. And I know I asked only for the solutions that are between 0 and 2 pi, but you'll see why in just a second. We will manufacture those in just a minute. So 3t, this angle, whatever this angle is, would be pi over 3 plus 2 pi k forever. Or it could be 5 pi over 3 plus 2 pi k forever. So what I'm going to do is I'm going to divide both sides by 3. Okay, I'm going to multiply this side by 1/3, divide this by 3, multiply this by 1/3. Okay, what I get is that my solutions will be pi over 9 plus 2 pi over 3 times k, or t is going to equal 5 pi over 9 plus 2 pi k over 3. Now let's look at, let's call this t sub k. Let's look at the different t values that this will yield. Of course, 2 pi over 3 is 6 pi over 9. So my solutions will be pi over 9. Then I'll add 6 pi over 9, which gives me 7 pi over 9. Then I'll add 6 pi over 9 again, which gives me 13 pi over 9. I want to stop once I hit 2 pi, which is 18 pi over 9. If I added another 6, I would go out to 19 pi over 9, which is outside of that window of 0 to 2 pi. Now my other equation will yield me 5 pi over 9. I'm going to add 6 pi over 9, which would give me 11 pi over 9. I'm going to add another 6 pi over 9, which could give me 17 pi over 9. And if I go further, I'm going to, again, run into an issue. So here are my 6 solutions, right? We took the 2 solutions we would normally find between 0 and 2 pi, and we tripled the number of solutions because we did a horizontal shrink by a factor of 3. Okay, let's look at the other equation on this slide here. All right, so let's go ahead and isolate tangent of x over 2. So let's subtract 3 and divide by 3. That means that the tangent of x over 2, we want to know where it equals -1. Well, let's look at a graph of tangent of x over -2. So the period of tangent normally is pi, but we're going to divide it by b, which is 1/2, right? So now what we're going to have is a period of 2 pi. So we're going to go from -pi to pi. All right, now if I want to know the solutions between 0 and pi, the graph of tangent is going to look like this. I don't care, based on the solution set I'm looking for, I don't care about anything in yellow here. All right, I want to know where the tangent x over 2 equals -1, which in this case will not happen at all on this interval from 0 to pi. Okay, where it's going to happen is on the interval between the next 2 vertical asymptotes, which would be pi and 3 pi. Okay, so our graph will look like this, and what we're looking for is where this red line crosses that graph. We're looking for that solution. We're going to get one solution between 0 and 2 pi. Of course, this being the point 2 pi comma 0. Okay, so let's find the coordinate of that blue point. All right, so where is the tangent equal to -1? The tangent is typically equal to -1 at, what would that be, 3 pi over 4, or x over 2 is equal to 7 pi over 4, right? Tangent is negative in quadrants 2 and 4. Okay, so if I were to do some manipulation and multiply both sides by 2, it looks like x would equal 3 pi over 2, or if I multiply this one by 2, I would get x equals 7 pi over 2. Now, 7 pi over 2 is not within that window from 0 to 2 pi. It's outside that window, so this is not our solution. So our solution ends up being x equals, 3 pi over 2. Okay, guys, this would be the the coordinate 3 pi over 2 comma -1. That is it for solving trigonometric equations using many different types of strategies. But the more practice you get, the better you'll get at it. So go ahead and jump into the homework and scratch through them and see what you can do. Let me know if you got any questions. Have a great day.